All right, and we are back for another video here today talking about exercise 1.7, which is on other algebraic functions. So just as a recap before we get into this, what exactly are polynomials? So polynomials are expressions or equations. So just remember, difference between an expression and an equation. If there is no equal sign, it's an expression, and as soon as I add an equal sign, it becomes an equation. Okay, so these are expressions or equations that contain a finite sum of variables in which all of the variable powers are positive whole numbers, also known as natural numbers. With this n here. So as some examples, we can see we have here a polynomial equation of degree 1. Why is it degree 1? So you can see here we have just an x here in the equation. We have 3x, that's x to the power of 1. The highest power of the variable in this equation here is just 1. So this is of degree 1. It's a polynomial. Why is this one a polynomial? So we can see this is an expression. There's no equal sign here. If we look at the variable powers, we have x to the power of 1, y is to the power of 5. They're both positive whole numbers, so there's no issue there. Doesn't matter that these coefficients are square roots, doesn't change anything. Same with this one here. You can see there's an x, there's a y. They're both being raised to the power of positive whole numbers. There's x to the power of 2, y by itself. Okay. You can see constant by itself, that's still a polynomial. You can see here we could have a, b, c's, we can have b's, we can have pi's as the coefficient, they're all fine. Now what about things that are not polynomials? So let's have a look over here. Why exactly is this not a polynomial? So we can see this is -4 times x to the power of -2, and I've said here that the variables need to be positive whole numbers. This is a negative power, so therefore this is not a polynomial. This one here, same thing. This could also be written as 5 times x to the power of -1. So x to the power of -1, that just means 1 over x. It's the same thing, just like this one over here could be written as -4 over x to the power of 2. So as soon as the indice is down the bottom, that's the same as a negative indice. So x to the power of -2 is the same as 1 over x to the power of +2. And then same with this. Now over here, we can see we've got 2 times the square root of x. Now the square root of x, if you recall, the square root of x could be written as, just try and bring this up. So the square root of x could be written as x to the power of 1/2. So we can see here the power is not a positive whole number. It's in fact a half. So therefore that's not a polynomial. Same with this one. This here, we have the power of a fraction, also not a polynomial. This one here, again, that's the same as before. This is just x to the power of -2, not a polynomial. You might argue with this one here, by the way, that we could rearrange this. We could rearrange this equation here, and we could say that this could be written as y times x squared is equal to 1. So what's the issue here? We can see that we've written this in the form of a polynomial of degree 1. Sorry, we've written this in the form of a sum where the polynomial, where all of the powers of each of the variables are positive numbers. So it can be a bit tricky. Sometimes something might look like a polynomial, but it's not. But yeah, we've written, like, if we write it in the standard form of a function, we can see that y is the output value here. So written in this form here, we can see that there's a negative indice. So this is in fact not a polynomial. That's what I'm trying to get at. So it can be a bit confusing sometimes. But yeah, anyway, we have x to the power of 1/2, 3/4, not positive whole numbers, so not a polynomial. This is a circle, that's also not a polynomial. And then we have here a cube root power, not a polynomial. Okay, so anyway, moving on. So in general, polynomials contain terms in which all of the terms are of the form a times x to the power of n, so where n is the input value, and a is a real number, n is a positive whole number, x is a variable. So we'll be looking today at other examples of non-polynomial functions. Anyway, that notation aside, those definitions aside, let's move on. So So an important concept that you need to be aware of is the concept of maximal domain, also known as implied domain. These terms are going to be used interchangeably. This is the set of inputs. So remember the inputs, the x values, for which there is a defined output, which is the y value. Okay, so what you need to be careful of whenever we're dealing with functions, we're just looking at two things. So are there any values of x for which the denominator is 0? So in other words, what we are not allowed to do, we are not allowed to have this value down the bottom if we have the equation y equals 1 over x, for example. The value of x cannot be equal to 0 because we're not allowed to divide by 0. So any value for which the denominator is 0 is going to be undefined, and also any value that creates a square root of a negative number, for example, negative x. So let's take, for example, the equation y is equal to the square root of x. This is only defined when x is greater than or equal to 0, because if x is less than 0, we have the square root of a negative number, and those aren't allowed in mathematics for the purpose of methods. Okay, so the implied domain of, let's say we have two polynomials. So this is kind of just extrapolating from this. If we have two polynomials, so x squared plus whatever divided by x cubed plus whatever, where fx and gx are polynomials, is what? Let's see if we can figure this out. So this is an open-ended question. So the implied domain, it will be defined so long as g of x is not equal to 0. So it will be defined for all x, so we can write that like that, for all x such that, so we could write such that g of x is not equal to 0. Something along those lines, just so long as you make the meaning clear. Same with this one here. So it's defined for all x. So for all x, sort of like an upside down A means for all, such that f of x is greater than or equal to 0. So the square root, the thing underneath the square root cannot be negative. And then finally, if we combine these two things, so let's say if we combine these two things, now if we look at that one there, the square root of f of x, that needs to be greater than or equal to 0, right? So we might think that the answer is f of x must be greater than or equal to 0. However, given that in this case, we have a division of the polynomials, the denominator down here, that can't be equal to 0 because then we're dividing by 0. So in fact, this is not the answer. It's actually when f of x is strictly greater than 0, because f of x cannot be equal to 0. So we have kind of two restrictions. We have f of x needs to be greater than or equal to 0 to satisfy the square root component, can't be negative, and also f of x cannot be equal to 0 because we can't divide by 0. And then if we combine these two facts together, we get the overall implied domain of something of this form, which is that the f of x must be strictly greater than 0. So we're just kind of combining these ideas in our heads. It'll come back later. All right, so continuing on, let's see if we can do a little bit of practice. What is the implied domain of these two equations? So first one, we have a square root. So like we remember, the thing under the square root sign needs to be greater than or equal to 0. So we've got this rule. So now all we have to do, so this is A, all we have to do is do a little bit of algebra to rearrange this. So the first thing I'm going to do is I'm going to plus 4x to both sides. That gives me 3 is greater than or equal to 4x. And then the second thing I need to do is divide both sides by 4. So that gives me 3 over 4 on this side and x on this side. And then written in what is traditional, which is having the x first, we would then write this as x is less than or equal to 3 over 4. Notice the order of this inequality is very important. If you get it the wrong way around, your answer will be wrong. Okay, so that's the answer to that first question there. Let's have a go at B. So we can see here, when is this one not defined? So this is not defined when x minus 4 is equal to 0. So when is x minus 4, the thing underneath this division over here, when's that equal to 0? Well, that's equal to 0 when x is equal to 4. We can plus 4 to both sides. We get that as our answer. So is that the answer? No. So we're after the implied domain. So it's always good to reread the question after we do it. So this is defined So let's say defines for x, so for all values of x, except for 4. And as I mentioned in class, it is extremely important that you get this notation correct. The slash needs to go in this direction. If you were to draw it in that direction, then you'll get the answer wrong. So that there is the answer. So the way you read this is x. X is an element of all real numbers. So x is allowed to be any number except for the element of 4. So x just can't be 4, it can be anything else. And that's the implied domain or the maximal domain over which the function is defined. All right. Now, the next part of this chapter, next part of the exercise rather, is looking at a bunch of different types of polynomials, so non-polynomial functions, and then describing a few of the key characteristics of these. So I'll just go through these and I'll do a few examples at the end. So the first one is called the rectangular hyperbola. It looks like this, y equals 1 over x. Why is it called a rectangular hyperbola? I've got a little note here. This is called a rectangular hyperbola because the asymptotes are perpendicular to one another. So you could actually have a hyperbola that looks like this, for example. So let's say we have two asymptotes. So these are just points where the function is not defined. We use dotted lines for them. Those of you who've done specialist might remember seeing hyperbolas that look like this. This would be a non-rectangular hyperbola. You can see that those two asymptotes are not perpendicular. So remember, perpendicular, it's like a right angle. The two asymptotes are at a right angle to each other. In this case, they're not. So you can see there, that is still actually a hyperbola. So these lines here are getting ever so close to those asymptotes, but they're never quite reaching them. So it's still a hyperbola. However, that would not be a rectangular one. In methods, we only look at rectangular hyperbolas, so that's not something you need to worry about. That's just a quick little note about why it's called rectangular hyperbola and not hyperbola. So, basic form of hyperbola is of this equation here, y equals 1 over x. The maximal domain is x is an element of all of the real numbers except for 0, because if we divide by 0, we're breaking maths. So we can see here the key features of this type of equation is that there's a vertical asymptote at the points x is equal to 0, and there's also a horizontal asymptote, that's this one over here, and that has the equation y is equal to 0. So there are two key features. As x goes to infinity, y gets incredibly small and it approaches 0, it never quite reaches 0. That's what the asymptote means. We call this asymptotic behavior. Similarly, as x tends towards negative infinity, over in this direction, y also goes to 0. So it gets really close to 0, but y is never actually equal to 0. So that's a key distinction. The range, if we were interested in the range, I've written the maximal domain here, but in the same way, the range is all of the real numbers, but excluding 0. So just keep in mind we have domain, x values, range is the y values. Okay, so yeah, I've got that note down here. We say the correspondence is 1-to-1, which means for every x value, there's a unique y value or a unique output for every input. All right, with transformations, and this is going to be a general trend that you're going to note, we have this equation. So the equation could be written as y equals f of x. And if we apply transformations to this, you're going to see the same pattern emerging every time. The function is going to end up looking like y equals whatever that function was times x minus h plus k. Consistently throughout this chapter, h is used as the horizontal translation, so moving it left to the right, and k is the vertical translation, so moving it up or down, and a is called the dilation factor, which is sort of squishing it or elongating it. So this is this is what a rectangular hyperbola will look like in general. A, h, and k are constants. You will need to find what those values are, and y and x are our variables. The asymptotes are occurring at x equals h, y equals k. And therefore, the domain is going to be all of the x values excluding h, and the range is all of the y values excluding k. So for example, if this graph over here gets shifted up, and now instead of being where it is currently, I'm going to chuck it up somewhere over here. So let's say that's now our asymptotes. So we've shifted that graph over here. Now we have vertical asymptote is occurring at, I think I've got these two the wrong way around, so that should be, no, that's right, yeah, that's all good. So yeah, we've moved this one over here. So now this asymptote here is occurring at a particular point. It's occurring at x is equal to h, and this asymptote up here is occurring at y is equal to k. Now this equation here, it might look like this. So it's an asymptote that's been shifted over there to the right and up. And now this equation, this orange equation, will have the form y is equal to, let's say, 1 over x minus h plus k. So you can see that there is the horizontal, that's the vertical. Just be really careful, there's a negative with the horizontal one, not with the vertical one. It's a little bit confusing. It has to do with transformations. The reasoning behind it is, yeah, I mentioned it in another video, but yeah, for now you can just remember the general format of these equations. So anyway, moving on. We've got truncus is the next one. So truncus has the basic form of y equals 1 over x squared, very similar to the hyperbola, it's just square down the bottom. It looks a bit like a hyperbola, but of course, whenever we square a negative number, we get back a positive number. So if I put in, for example, negative 1 over negative 1 squared, so negative 1 squared is 1 over negative 1 squared. That's just equal to 1. So that's just 1 over 1. So we get out a y value of 1. That's this one here. Okay, so it looks like a hyperbola, just with both pointing in the same direction. And of course, if we had, for example, y equals negative 1 over x squared, that would look exactly the same as this initial graph, just reflected in the x-axis, like so. Key features of a truncus are that it has a vertical asymptote at x equals 0. So that's the vertical asymptote here at x equals 0. And it has a horizontal asymptote at y equals 0, which is over here. It has a domain where it's defined for any value of x. So have a look, we can put in any value of x down the bottom here. We'll always get an answer so long as that x is not equal to 0. So that's why we say it's defined for all real numbers excluding 0. And it also has a range of just the positive real numbers. So notice it's not defined for 0. There's no way that we can have 1 over x squared, which is equal to 0. So there's an asymptote at y equals 0. But we could have any other value that is larger than 0. Or in the case of this orange graph over here, the range of the orange graph is going to be all of the negative real numbers. The domain of that orange graph will actually be the exact same as the black graph above it. Okay, so again, the correspondence is 1-to-1. For every input, there's a unique output. With transformations, the general form of a truncus is, is the correspondence 1-to-1? No, I think the correspondence here is many to 1. So I think this should say many to 1. So it's still a function. Every input maps to a unique output. But say, for example, if we take the points -1 and +1, if we put -1 into this equation, we get 1 over 1, which is 1. And if we put in 1, we get 1 over 1, which is also 1. We get the same two outputs. So there are many inputs that give us the same output as one another. In other words, it would fail the horizontal line test. Still a function because it passes the vertical line test, but yeah, correspondence is many to 1 here. So with transformations, the general form looks like this. We've just replaced the x with x minus h in this equation. So that x has been replaced with x minus h. The y has also been replaced with y minus k. So what I've done is, you can imagine that this is the same as y minus k, replacing the y, is equal to a over x minus h squared, replacing the x in this equation here. And we've just plussed k to both sides to get this form over here. And again, this is about the transformation stuff that we spoke about earlier. We get this form we can see that there are asymptotes that occur at x equals h and y equals k. The domain is all of the real numbers excluding h. The range is from k up to infinity. Okay, so you don't really need to know a lot of this. You just need to kind of know what the basic form looks like and how to apply the transformations and what these graphs kind of look like. So it would be useful to have these little diagrams in your book, just the main ones in black, so that you just remember what they look like. Square root functions, basic form is y equals the square root of x. That looks like this. It's a little bit like the top half of a sideways parabola. So you can imagine a parabola kind of looks like that. It is symmetrical. So there's a point of an axis of symmetry going down the middle like that. And what we've done is we have reflected this in the equation y equals x. So we've reflected that orange graph in the line y equals x. We only have the top half of this because if we had the bottom half, we would not in fact have a function, because again, every input needs to have a unique output. It doesn't happen if we have the bottom half there. It fails the vertical line test. So that's what the square root function looks like. With transformations, the general form of the square root function is this. I've just put in the b there so you don't really need to include the b. The textbook doesn't include it, but if you just think about the transformed version of this looking like this, it'll be easier for you, because I think most, if not all, equations you will deal with will look like this. So we've just replaced the x with x minus h, replaced the y with y minus k, and we've put it into this format here. You can see h is the horizontal dilation factor, k is the vertical dilation factor. The end point is going to occur at hk. The domain is h to infinity, so from here upwards. So you can see for this initial one here, the maximal domain was from 0 to infinity. If I put in, say, x equals -1, I have the square root of a negative. So we can't have square roots of negative numbers over here. And of course, this number out here, if there is a number underneath the square root sign, it needs to be greater than 0. Otherwise, we're going to have a reflection. It might be interesting for you to play around with that. So let's just have a quick look at how things might look. If we have a look at y equals square root of x, that looks like this. Y equals square root of negative x looks like this. So in that case, you can see that if I put in a negative value for x, I actually get a positive number underneath the square root sign. So for example, if x is equal to -2 or -4, we can see that's over here. X is equal to -4. Well, what we're going to end up with is -1 times -4, so that becomes +4, so square root of 4, which is 2. That's why we have this value here. However, if I put in, say, positive 4 here, we have the square root of -4, and that's not defined. So that black one is kind of like reflected in the y-axis. In the same way, I could put in this, so y equals negative square root of x, we could have y equals negative square root of negative x, and we've completed the various different reflections that we could have. So again, just keeping in mind how this function is defined will help you when it comes to graphing it. What will make it undefined? Think about that carefully. Okay, cube root functions. We have here cube roots. This is kind of new, but it is basically just a cube. So remember, a cubic polynomial, if, for example, we have y equals x cubed, that will look like this. It has a stationary point of inflection at the point 0, 0, and it's kind of like two halves of a parabola, but the two halves are going in different directions to one another. So they have kind of a funny shape to them. The cube root is that exact same shape, just tilted on its side. So what was the x-axis is now the y-axis. What was the y-axis is now the x-axis. It's the inverse. This is what the inverse means. We've just swapped the two axes with each other. And you can see that there is the basic form of a cube root. It's defined for all real numbers because we are actually allowed to have the cube root of a negative number. So the cube root of -8, for example, is equal to 2 because 2 to the power of 3, so -2 to the power of 3 is equal to, well, let's think about it. So -2 times negative 2 is 4, and then 4 times negative 2 is negative 8. So it ends up being a negative answer, which means that the cube root of negative 8, what number do we times by itself 3 times to get negative 2? To get negative 8, that is in fact just negative 2. Okay, so we can see that in this case, doesn't matter if the x value is positive or negative, we're always going to get a defined output. The feature of the cube root function is that there is a point of inflection. It's not a stationary point of inflection. We'll discuss the difference. What's not necessarily a We'll discuss the difference later anyway. Don't worry about that too much. There is this weird point of inflection, though. Point of inflection just means that there is a change in concavity going between it's sort of facing this way. So there's a parabola going this direction to a parabola going in that direction. So that's what we mean by a change in concavity. In the middle, the derivative is changing slightly. The derivative is not equal to 0 here. We'll discuss that when we get up to calculus. So for now, don't worry about the difference between point of inflection versus stationary point of inflection. Moving on, power functions. This is the last one. Power functions have the form y equals x to the power of p over q. These things here, you just need to be really careful. If the p value is larger than the q value, it's going to look like your classic polynomial where everything is sort of going upwards. And then if the q is greater than the p, then we have like a square root shape. So for example, if it was y equals x to the power of 3 over 2, that's going to look more like this graph here. But if, for example, it was more like, let's say, y equals x to the power of 2 over 3, the number down the bottom is bigger than the number at the top, so it's going to look more like that. And if the two numbers are equal to each other, we just have, for example, x to the power of 3 over 3. 3 divided by 3 is just 1, so that's just y equals x. So that's this just a straight line, basically. So we don't go much further than that. Power functions, they rarely come up in exams. It might be like a multiple choice question. So just something to keep in mind. If the number at the top is bigger than the number down the bottom, it looks like this. If the number down the bottom is bigger than the number up the top, it goes to the side instead. All right, so let's do some practice questions. So question 1, determine the equation of the following graph. Okay, so let's find ourselves a little bit more space down here. Let's give this a crack. So first up, when we have a look at a graph like this, we first need to figure out what type of graph is this. This kind of looks to me like a rectangular hyperbola. So I'm thinking about this equation here, y equals 1 over x. That's my starting point. I'm also going to look at this and I'm going to see where the asymptotes are occurring. Well, maybe going back a little bit, we know that this equation with transformations will look like y equals a over x minus h plus k. To find the equation of this graph, all I need is an a, an h, and a k. So let's see if we can figure out what those values are. H is the horizontal translation. So the asymptote has been shifted over here. We can see that initially this asymptote was at the point x equals 0. So going back to the basic form of a rectangular hyperbola, there's an asymptote at x equals 0. Now the asymptote's over here at x equals 2. So we can see h must be equal to 2. And in the same way, k is the vertical translation. So if we have a look at this graph, this asymptote here, it was initially up here at y equals 0, and it's been shifted down to y equals negative 4. So k is equal to negative 4. So let's put those two facts together, and now we can say that the equation must be of the form y equals x minus 2 minus 4. Need to be careful with these negative signs just because we know for a fact that this is a negative sign here associated with the h. Okay, so now to find the answer, all we need is to figure out what a is equal to. So let's put this together. We're going to use the final piece of information, this point here, 0, 0. So we will use 0, 0 to find a. So let's substitute it in. we're just going to put in 0 is equal to a over 0 minus 2 minus 4. Rearranging this, we get 4 is equal to a over negative 2. We can rearrange this. Again, we multiply both sides by negative 2. A is equal to negative 8. So therefore, our answer for our final graph is y is equal to negative 8 over x minus 2 minus 4. And the reason that this is a negative sign here, we can see that that makes sense because initially the graph would have looked like this, where sort of pointing that direction. You can see that it's on the positive side of that first quadrant part over here, and the third quadrant part is facing like that, just like in our initial basic form of the graph. It's going like this. However, if we put a negative sign there, that's going to flip this so that it will look like those two lines are going up on the other side of each of the asymptotes. So that's a reflection there. So because there's a negative sign there, that means that there's a reflection in the graph, and that makes sense with what we can see there. Okay, moving on. So we want to now sketch a graph. So how would we go about sketching a graph and then stating its domain and range? So when it comes to sketching a graph, we need to remember to always include intercepts and asymptotes. Very important for you to remember to do this. So let us attempt to do so now. First up, let's have a look at this equation. That looks like a truncus to me because we have something like this. So we know truncuses look like this, y equals 1 over x squared. All right. Now this truncus has asymptotes at, well, let's have a think about it. So we had that form. It's been transformed by some a, h, and k. So it needs to have that form there. So we have a horizontal translation factor of h, vertical translation factor of k. It will have a horizontal asymptote at, a vertical asymptote at x is equal to 3 and y is equal to 8. So positive 8 because it's been shifted up. Okay, so that's our first piece of information. All right, so with that in mind, we now know where our first two asymptotes are. So I guess we can just go ahead and do that. So what I'm going to do is I'm going to draw up our two axes. So we have x and y axes, and this is not the best stylus to draw this with, but let's see how we go. We can see that there's an x asymptote at x is equal to 3. So x is equal to 3. And then up here, there's another asymptote at y is equal to 8. Okay, so next thing we need to do is have a think about, is this hyperbola going to look like that, or is it going to look like that? So to do that, we'll have a look at this. We can see there's a negative sign there. So that means that these two lines are going to be pointing in the other direction. So instead of looking like that, it will in fact look like this. So now we've got an idea about how this graph looks. Oh, I'll get rid of that other blue line there. So that's y equals 8. Oh, let's go back. All right, so we can see that the graph is going to look like, I'll just leave that in blue. It's going to look something like this. So it'll go like that. And then on the other side, it will go like that. So to finish this up, we need to figure out what this intercept here is and what this intercept here is. So let's find the x and y intercepts. So I'll go back to red for that. So find intercepts. So first up, let's find the x-intercept. To find the x-intercept, we let y equal 0. So I'm just going to replace y in this equation here with 0. So x-int, we have 0 is equal to, it was 8 minus 2 over x minus 3 squared. I believe that's correct, yep. And then we're going to rearrange this to make x the subject. So first up, we will add to both sides. Second up, we can maybe times both sides by x minus 3 squared and then divide both sides by 8. So we can swap these two numbers around. If we remember our algebra, we have x minus 3 squared is equal to 2 over 8, which is the same as 1 over 4. And then we can square root both sides to get rid of this square. We have x minus 3 is equal to plus or minus 1 over 2. And then we can plus 3 to both sides. So x is equal to, that's going to be 1 over 2, so plus or minus a half plus 3. So if we make this one here have the same denominator, so this is going to be a half, so let's say plus or minus a half plus 6 over 2, that's going to be equal to, so 7 over 2. And if this is negative, we have 5 over 2. All right. Now, which of those answers is correct? Let's have a look at this shape. So we can see that this x value is larger than 3. So therefore, it must be 7 over 2, because 5 over 2 is less than 3. That's 2.5. So this value here, or this intercept here, that must be 7 over 2, 0. That's our first intercept. So I'm going to circle that one as our answer. 7 over 2. Ooh. Why is that so hard? There we go, 7 over 2. All right, so now let's go back here, find the y-intercept. So the y-intercept, that's going to occur when x is equal to 0. So let's substitute it in. We have y is equal to 8 minus, going back to this equation at the start, 8 minus 2 over x minus 3 squared. Okay, and I'm making x equal to 0. So in fact, I'm going to write this as 0 minus 3 squared. All right, and now we just solve. So this is going to be equal to 8 minus 2 over, 3 squared, negative 3 squared is just equal to 9. So that's going to come out as, 8. We need to write that as something over 9, don't we? So that's going to be 72 over 9 minus 2 over 9, because 72 divided by 9 is equal to 8. And then that there is going to be equal to 70 over 9. So therefore, our intercept just up here is going to occur, that value there, that point where where this line, the hyperbola, crosses through the y-axis, that is going to occur at 70 over 9. So 0, 70 over 9. Done. Okay. That's how you answer a question like that, and you'll do it a little bit neater than how I've done it there with the stylus. Okay, so last question. We need to sketch a square root function and state its maximal domain. Let's do the maximal domain part first. So domain, that is going to be when x is greater than or equal to 4 minus x, because the thing under the square root sign can't be negative. Okay, so let's rearrange that. Change that. When 4 minus x is greater than or equal to 0 is what I should have said there. Okay, so that thing must be greater than or equal to 0. Okay, so if we rearrange that, we have 4 is greater than or equal to x. That's our maximal domain. Cool. Okay, so now let's sketch this function. So we can see, or we remember, that a square root function, it kind of looks something like this. Okay, so it's got like a sideways parabola. There's no negative sign over here, so it's not going to be down underneath this, like so. However, we can see that there's a negative sign in front of the x, so it's defined for all, if I write this the other way around, it's for all values of x that are less than or equal to 4. So in fact, what's going to happen here is this graph is going to start, it's going to start at x is equal to 4, and it's going to go backwards, like so. So it's going to look something like this. It's going to look something like that. So we have, that's y, that is x, And we can see that there's going to be some kind of intercept here. It's not necessarily going to start down there either, is it? So we can see here it was that basic graph and it's been shifted up and down. So it won't quite look like that. Let's see if we can figure out what the endpoint is. So the endpoint occurs at, well, remember, so it's of the form y equals square root, like let's say y equals a times square root of x minus h plus k. The endpoint occurs at 4, -1. So let's see if we can look at where that will be. So 4, -1, that's going to be somewhere. So 4, -1, somewhere here. So that's 4, -1. Starts there, and it takes on this kind of shape. So it's going to look something like that. So a sideways parabola, we're looking for an x-intercept and a y-intercept. So let us find those two coordinates. So first up, let us find the intercepts. So say the x-intercept. So find ints, we have x int is let y equals 0. So y equals 0, then we have square root of 4 minus x minus 1. Rearranging this, we have 1 equals 4 minus x. Square both sides, we have 1 equals 4 minus x. And then we're going to maybe minus 4 from both sides. We have -3 equals -x. And now we're going to make both sides positive. X is equal to 3. Okay, so we have x-intercept at x equals 3. Looks about right. And then we're going to find the y-intercept. To do that, we let y equals 0. So we let x equal 0. So we have y is equal to the square root of 4 minus 0 minus 1. That's equal to the square root of 4 minus 1. Square root of 4 is just 2, so 2 minus 1, and that's just 1. So that's our y-intercept right there. So 0, 1, and we're done. That's all we need to include. So the endpoints and the two intercepts. And in fact, I will write that there. So always include asymptotes, intercepts, and endpoints. So don't forget to include those as well. So that is this video. Hopefully that helps you a little bit with 1.7. Let me know if you find these videos helpful, and I will see you guys in the next one. See you later.